Hi everybody, welcome to the last, that's right, the last of our practica for the semester. So this is your last GIS Wednesday, and I know you're going to be sorely disappointed. We've kind of saved one of the most fun things for the last, at least in my opinion, and what we're going to be dealing with today is 3D point cloud generation from unordered imagery. This is the technique that we talked about yesterday, falling under the general category of photogrammetry, but specifically it's the technique that's sometimes called structure from motion, and other times called multi-view stereo. Sometimes interchangeably, and sometimes people make a distinction between those. But either way, the point is to use a bunch of unordered photographs to make a point cloud like the one that we're looking at here. Now, what we're not going to go through today in detail is the process for actually extracting the points, because well, it's rather involved in some ways, and there are actually a variety of tools available to do it, and there's actually quite good tutorials to do it online somewhere. And just doing that would sort of be a whole practicum on its own, but we only have the one left, so rather than do the sort of boring part of software extraction, we'll do the more exciting part of dealing with the data after we've done that. Now, we're going to work with data that was created or extracted using OpenDroneMap. This is my new weapon of choice for structure from motion stuff. It's really flexible. It produces probably the best output of any of the available open source methods that I've used, especially considering that it comes out geo-rectified, which means we can bring it into a GIS and we can do all kinds of stuff with the output from this process. Now, it's tricky to run. It runs only on Linux, and you got to set it up properly, and you got to put the right parameters in. So if you're curious about that kind of stuff, it's something we can work in one-on-one sort of later on at another time. But for now, we're going to work with a project that I've already run through OpenDroneMap. So I have the information over here. But before I talk about the project and how I got it to work with OpenDroneMap, I'm just going to show you a couple more options for software that you can use. Like I said, this one currently only works on Linux, so if you don't have Linux, you might be able to get something like this, although maybe not quite as useful in terms of it not being geo-rectified, that kind of stuff, with one of these other pieces of software. The first one I would recommend for you is this one called Visual SFM, a visual structure from motion system. This runs on Windows and Mac as well as Linux. It's pretty useful. It's pretty easy to run. There's a good some video tutorials and some documentation on the download page. Like I said, it doesn't come out geo-referenced, which is its sort of one downside compared to OpenDroneMap, and it's not technically fully open source, meaning we can't get the full source code, although we know that it uses some open source tools here. So it's only sort of pseudo open source. Nevertheless, I still recommend using it, especially if you're using Windows or Mac. This is probably your first stop. A previous thing that I used to recommend was the Python Photogrammetry Toolbox, and it used to work really well, although it doesn't seem to have been developed in the last little while. So you can still try it. It runs also on Windows as well as Linux, but I don't know how much success you're going to have with it, so I'm just putting it out there. And one of the most kind of exciting things, another really recent one, is this TheaVision library. Now, this is for the computer nerds, because this is all command line and you got to program it a little bit. But this may be the latest generation of, at least it's one of the most recent advances in this sort of structure for motion stuff that's out there. So those are your options. I would sort of point you in the direction of Visual SFM. Personally, I think OpenDroneMap is better, but this is probably easier to use for you. So give that a try if you want. We can talk about that at a later date. Okay, to the data. Originally what I started with was just a series of images taken from a drone, and I'll just open them up so you can see what they are. Now this is actually this was drone footage taken very recently at the Nate Harrison site that many of you have been working at during the whole semester. You can see here this is a bedrock outcrop with some probably bedrock mortars visible here, and we have some drone images. So I'm just going to scroll through the images, and you can see that these images are, they're pretty good. The they do some of the things that we want out of our images for this technique, which is that they move a little bit from side to side, giving some horizontal movement. You got to have that motion to do the structure from motion, and they have pretty good coverage of this bedrock. We've got a little bit of a shift here. We have a sort of zoom level, which is, not the greatest, but it's okay. We can still work with this data. The other good thing is there's a scale here, so we can check to see how well the georectification process using the GPS data from the drone worked. And that's the other thing I want to point out, is that this drone, this image taken from this drone, has tags from the GPS that's inside the drone. Now what we're looking over here are what's known as the EXIF tags. This is the metadata that's attached to the header of the JPEG imagery files. There's all kinds of stuff, so we can look at the exposure, of the shutter speed for taking the cameras, the f-stop, which is the aperture, the focal length, and a bunch of other stuff. So this is really important to have this data, both all of this stuff in here about the camera and the focal length and the shutter speed and all the stuff like this. But also to have the GPS information in the header here. Given these two bits of information, the focal length and all that kind of stuff, and the GPS, OpenDroneMap and other structure for motion and photogrammetry software can both orthorectify the imagery, unwarp it due to the bending of the focal length and the lens and all that kind of stuff, but it can also georectify it a little bit based on knowledge of where the camera was in space when it took it and the altitude, right? So it's got latitude, longitude, and altitude. So that's really cool. That's going to be real helpful, and it's going to let us get a full georectifying model that we can bring into GIS afterwards. Okay? All right. So those are the images that we have to work with. So 15 images or 20 images or something like that. Not very many, but it's enough for our purposes here. And essentially what I did is I ran it through OpenDroneMap. I followed all the directions to get it installed and all that kind of stuff. And OpenDroneMap produced all the remainder of all of these folders, right? So I started just with this one folder, and OpenDroneMaps did all the rest. So first thing it did is resize the images, and then it ran through structure from motion to create the depth maps and all the stuff that we talked about before. Ran through PMVS to get the dense point clouds, and then it created orthophotos. It made meshes, right? So it took the points and it connected them into a lattice network. It georeferenced all of those things, and then finally it added the textures, the actual colors from the photographs back onto it. So at the end of the day, all of these things are great. They all have their uses, but the final products are going to be an ODM_texturing and ODM orthophoto. So let's take a look at orthophoto first. There's two of them. The TIFF here is georeferenced. The PNG is ungeoreferenced. So we'll just open that first. And what we have here is essentially a reconstructed, stitched aerial mosaic of the whole area that's referenced to the geographic coordinate system in space and to scale, right? And supposedly it's looking straight down, but you see it's sort of slightly warped from the original images because it's stretched it over the topography and unwarped it due to the geographic distortions, but also to the photographic distortions. And of course we're missing a bunch of information here, and that's due to the fact that we probably didn't have enough proper images for this particular data set, and we could have done a more rigorous aerial survey, and this would have been all filled in over here. All right. So if we want to open this up in QGIS, we can do that. It will take a little bit of time to load up here. But when it does so, what we can see is, just give it a second here as it loads that up. There we go. And now we can do all the kind of stuff. We can digitize on top of this. We can identify the stuff. In this case, it's just imagery, so it's just bands here. We can measure distances, right? So we can actually figure out how many meters, right, if we go across it. So we can measure the size of the boulders, for example. Okay, so let's actually just check to see how good we did. This is a yardstick over here. And yeah, it's pretty good. It's not exactly perfect, but that's okay. 1.16 meters should be something like 0.9 meters. Maybe I'm not putting the dots in the proper spot. I'm pretty close. Yeah, so we're pretty close, right? So just based on the GPS information in the drone, we got pretty good. We could have gotten a better rectification if we had had ground control points and fed those into OpenDroneMap. But that's pretty cool, right? That's pretty cool indeed. So this is great. Already you can see the use of this kind of stuff. But this is only one of the potential outputs. What we're really interested in is the 3D information as well. So let's take a look at that information. And that is, well, there's 3D information in all of these things, including this over here. But the first one we want to look at is this one in ODM texturing, okay? And really we're going to look at this GeoObj file here. And we're going to do it in Meshlab. So I have Meshlab open in the back. This is the piece of software. Now, before we get into Meshlab, I'm going to point you to this wonderful YouTube channel. This is Mr. P's Meshlab tutorial. He's one of the developers of Meshlab and has made a just tremendous series of tutorial videos on how to use Meshlab. I mean, the knowledge that's in here is way beyond what we could get into in just even this one semester. So if you're into this, I highly encourage you to go and have a look at all of these videos and just go through all of the things, right? All of the things in here. And if you do that, you'll become an expert in Meshlab in pretty much no time flat. It's pretty amazing what you can do on YouTube these days, all right? So we're going to just scratch the surface with Meshlab. We're just going to take a look at a couple of things that we can do to render and view our imagery and to make it look a little nicer. So we're going to open it up. Here we are where I happen to already be in this folder here. So we'll pick our ODM textured model _ geo. That's the geo-referenced one. And it takes a little while to load. You see the progress bar. And here we are. So I'm using the mouse wheel. I can scroll in and out to zoom. I can click and drag anywhere to rotate like this. If I hold down the shift and I click and drag, I can zoom in and out. If I hold down the control and I click and drag, I can move it side to side, up and down, right? And this little sort of globe or these circular lines here kind of help us orient ourselves. So let's get a nice view. We can actually see the 3D information that's actually in here. So this is the final model. This has a bunch of data fused together. It has the photographs, the colors, the textures. It has the mesh, which is the smooth surface, and it actually has the points also embedded in it. And up here we can turn all of that on or off, right? So this little ripply thing here is to turn the texture on and off. That's the color of the photographs, right? So we can see that. The light bulb is to turn the light on and off in our viewer software over here. So it often helps to have it on. Sometimes we don't, though. This is the way we want to show our mesh. Do we want to see the facets, or do we want it to be smooth, right? Do we want to see the facets and the lines to help us see where the facets are? Do we want the facets in a nice purple color or the facets in a nice sort of white color? Do we actually just want to see the points, the actual points that came out of the model that was actually rendered? This will show us a bounding box, just showing us the general space that the model occupies, right? We can have the texture on, and we can change some things, the lighting and all of that kind of stuff, right? So this final model has all of that stuff. Some of the intermediate models only have some of those things. So one of the things we might want to do is to fill in some of these gaps. Oh, but before we do that, let's just double check that we get the same measurement. So I can pick the measurement tool over here, and I can measure across our yardstick. And here I got 1.18. So that's the same measure I got in QGIS. It's not exactly right for a yardstick in here, but it's pretty darn close. So we'll say it's pretty good. We would want to calibrate this a little bit more if we wanted to. We could do that in the filters over here, in probably this one over here where we have the transform scale, and we could basically figure out the difference between 1.18 and 0.9. Actually, let's just do this real quick. I'll just get a calculator over here. So we have our 1.18 divided by 0.9, and the scale is 1.3. So we can just put 1.3 here. Uniform scaling means it's going to apply it across all of these axes. Freeze to matrix means it's going to keep that information embedded in the file. So we'll just hit apply, and it has done that. And so if we zoom back out, I hit Control H. There's a whole bunch of shortcuts to do that, but you know, that's what you learn from watching those YouTube videos. And now let's measure this thing. Oops, let's measure this thing here, and let's see. Well, I messed it up a little bit. I must have done the math wrong, but in any case, in fact, that's totally what I did, and I did the math wrong. I divided them in the wrong way, so it should have been a number below 1. Anyway, well, what I would have done is corrected the scale, and this would have read exactly 1 if I'd done that correctly. Darn it. That's what I get for going fast, so sorry about that. Okay, so let's do some more very quick manipulations here. What we might want to do is to fill in some of these gaps, and we can get a lot of that stuff here under the filters tool. Now there's a ton of filters here, and I recommend again you watching those YouTube videos if you want to know what they all do, but there's so many in here. We're going to go to this one here, is remeshing, simplification, and reconstruction. And we're going to go down to surface reconstruction. There's a couple of different ways to do this. We can do ball pivoting, and we can do Poisson. So let's just try Poisson for now. It's a simple-ish one here. Now, you should be optimizing all of these things, and there's data about how to do that, but we're just going to take the defaults, and we're going to run, and we're going to see, oh boy, that didn't quite turn out the way we wanted to. So what we can do is turn the layer on over here, so we have 2 layers. We have our original mesh over here, and we have our Poisson mesh. We can get rid of that by right-clicking and delete that mesh. And we can go back to our filters. We can do remeshing and simplification, surface reconstruction, ball pivoting. This is going to be a better one over here. So we'll just hit apply. It'll run a little bit in the background, so you see it marching along down here, 84, 85%. So you can see this is probably already going to turn out a little bit better because it's a more computationally intensive measurement. So let's see how it goes. There we go. And now we can see it actually added these areas here. And if we put our lighting off a little bit and get our grid back on it, we can actually see, a little bit the reconstruction. So all these dark areas, those are the areas that got filled in, right? So we did a pretty good job of filling them in. We got extra points, data points in those areas. So that's pretty cool. I'm pretty happy with that. Yeah, I think that's pretty good. We would at this point potentially have to retexture the object here. We could also reload the thing on top of it. In fact, like that. There we go. Let's Control H. Oh, I messed this up because I did the Poisson thing beforehand. Anyway, so the point is that we can very quickly fix our object that we had here. We can fill in some of the gaps in the model over there. Okay, so that's it for Meshlab. Again, we're doing this kind of quick. I realize that. There's all kinds of ways to clean up and mess with your meshes, but that's for another day. One of the other things we might want to do is to bring this data into GIS and potentially turn it into a DEM. And there's a variety of ways that we can do that. We can bring in the PLY or this .las that's from the georeferencing file over here. We can bring that directly into GRASS, right? So let's try doing that and see how far we get. So I'm just going to start GRASS up. GRASS 72. And I'll tell you what I'm going to do is just do it in an XY location. So I'm going to do this unreferenced for the moment because I would have to set up a location. Actually, we can bring it into the lat long location. Let's do that. So let's make a new one. Just call it test SFM. Click OK. Start GRASS up here. And now we'll go to import some data over here. And there's a variety of ways that we can do this, but the easiest way is to do LAS, r.in.lidar. So the LAS file format that we're seeing over here is actually the same format as a LiDAR point cloud. So we'll just browse to that over here. I have to go back to that file, LAS. And here we go. We're good here. We can give it a name, test point cloud data, and we'll just let it do everything on its own, right? Let's do this at well, we'll just leave it. We'll leave it and see what it does. Okay, let's see what it's telling me. Oh, it's actually in UTM zone 11. Okay, that's cool. Let's set up our grass that way. Do it the proper way, right? Let's do it the proper way. So let's make a new location. And let us select all the stuff from a list. So UTM and zone 11, it's north, and we'll search for WGS. 84 is what it was. Click OK. We'll click finish. No, it's okay. That's okay. So let's start grass up and do that all again. All right. File, import raster data, r.in.lidar. We'll browse to our LAS file. And there we go. Point cloud. What we needed to do is to override. Let's see, where is it here? We should have set the region to match. Let's see. Where is that option? Just that point cloud static. Transform. Oh, you know what it is? That's the one right there. Scan data. For cloud. Overwrite. Okay. So now what we have to do is to use these things to set our region. So let's go to region, set region, bounds, and let's see, we have 328 and 337 here. So 8328, 8337. So that's the northern bound. That's the southern bound. And let's see, that's the 9110. That's the eastern edge. And this is the western edge. Here we'll just set our region resolution to 0.1, so 10 centimeters. And we'll just hit run over here. And now we'll uncheck that thing. There we go. Alright. So let's zoom to that selected map. So we have a whole bunch of points in here. Crazy amounts of points. What we need to do is to expand this to become a DEM. So we'll do what we did before when we were doing interpolations. We'll do resample using multiple methods. That's rresamp. I picked the wrong one, sorry. Resample using multiple methods, rresamp interp, and we'll just call this DEM over here. We'll pick the method, we'll call bicubic, and Just hit run. And now we should have a DEM. Is it running? Alright, let's instead use interpolate surfaces, and we'll do it from vector points. We'll do a little thing first. We'll do a map type conversion of raster to vector. We'll take our test point cloud and we'll say points, and we'll call it points, and raster values at Z coordinate. We'll just hit run. Now we have a bunch of points. vsurf bcloud will put points. We will leave all of this the same, except we'll do that, and we'll hit run. Oh, we have to put an output name. Where is the output name? Output here. Output raster map. We'll call that DEM. Actually, settings, output map. We'll call it DEM, and we'll overwrite that, and we'll hit run. There we go. Now we have a DEM. Alright, so what we can do is to view that now in 3D. And we can see our really lovely, wonderful 3D output, right? It really makes a nice smooth one because we used not a great interpolation routine, honestly. We did it quick and dirty, but that's okay. That's okay. Sometimes it's okay to be quick and dirty, right? So let's put that here. Let's increase our resolution so we can see what we really did. There we go. And we can view it from different angles, right? So that's pretty cool. So we can basically see this is where the big bedrock outcrop was. This is, really smooth approximation because, again, we changed a little bit of the resolution, and we did smooth it with the interpolation. So we get a general surface contour rather than all the lumpy point cloud type stuff that we saw in Meshlab. So that's kind of the point of doing this. You get a nice smooth continuous surface for this area. Alright, so I think that's all I wanted to show you guys for now. It's a real rough and tumble intro in one practicum to all this crazy stuff. We'll talk about this in class tomorrow. We'll get a better sense of what we can do. Alrighty, see you tomorrow.